Newton's ideas on light were very revolutionary. I mean, what he discovered and now accepts was that normal light is made up of different colors of light.
This particular discovery concerning light and colors explained why the sky is blue, why there's a brilliant red sun at sunset, and so on.
If I have seen further than others, it is because I stood on the shoulders of giants.
This is a colossus. Men like Einstein, when they picked up Newton's works, were overwhelmed. One is overwhelmed with the capacity to assimilate this vast knowledge.
He was a genius of extraordinary caliber. In my understanding of things, genius of that order imposes certain penalties.
There was little cheer to be found in England on Christmas Day, 1642. The country was at war with itself. The forces of King Charles I and Oliver Cromwell were waging a fight for the hearts and souls of a divided people. At Woolsthorpe Manor in the county of Lincolnshire, the birth of a premature baby was greeted with a sense of impending doom. Only 3 months earlier, the child's father had died, and he was given little chance to live. To everyone's surprise, the frail child survived. His mother Hannah baptized him Isaac Newton after his deceased father. In the hope of securing a more stable future for herself and her child, Hannah accepted a proposal of marriage from Barnabas Smith, the rector of the adjoining parish of North Witham. Isaac, now only 3 years old, was left with his grandparents. For the next 8 years, Isaac saw little of his mother. On the death of his stepfather, Isaac's mother returned to Woolsthorpe. Now financially secure, Hannah made plans for Isaac's education as a future gentleman farmer. He was sent away to King's Grammar School in Grantham. An introverted and reclusive student, he made few friends and appeared to take little interest in his studies.
Being a smaller boy in the school, he was attacked by the school bully. But in spite of his small stature, he rounded on the bully and gave the bully a thrashing. So there is that incredible steely toughness that runs through him.
Isaac roomed with Mr. Clark, who ran an apothecary shop. Seeing Isaac's interests in the mysteriously labeled bottles and bubbling cauldrons, Clark showed him how to mix potions and gave him access to his books. Isaac's favorite book became The Mysteries of Nature and Art by John Bates, a book full of recipes and schematics for mechanical toys. Soon he was hand-building kites, model windmills, and even a water clock. Newton had discovered a refuge from the misery of his loveless, lonely life. He began to excel at school and quickly rose to the top of his class. When Isaac turned 17, Hannah recalled him to Woolsthorpe to run the farm. Henry Stokes, Isaac's teacher, aware of his budding genius, pleaded with her to let him stay on and apply for university. Reluctantly, Hannah agreed. In 1660, Stokes' star pupil was enrolled at Trinity College, Cambridge.
Teaching in Cambridge in those days probably wasn't very advanced or sophisticated by present standards, and many students would have to learn things by themselves. I think the formal instruction was rather limited, and Newton probably learnt much of what he did on his own.
With no financial support from his mother, Newton had to work his way through college, performing menial chores. While other students indulged in a vigorous social life, Newton rarely socialized. Instead, he pursued his unquenchable thirst for knowledge. In the course of his endeavors, he came across the mechanical philosophy of René Descartes.
Everything should be thought of in terms of a machine, working parts in contact with one another. So, for example, the planets were thought to move in gigantic swirling vortices of some sort of invisible matter.
Newton's interest in Cartesian philosophy brought him into contact with Isaac Barrow, the Lucasian professor of mathematics. Under Barrow's gentle tutelage, Newton was introduced to Galileo's ideas on motion and gravity, Kepler's laws of planetary motion, and Descartes' revolutionary work in algebra, la géométrie.
Geometry concerned itself with shapes and triangles, and what Descartes did was to regiment it, organize it, to decide everything could be done by measurement and by mechanical calculation.
The study of Descartes' algebra changed Newton's life forever. He fell in love with mathematics. What little interest he showed in daily college life was now subsumed in a passionate frenzy of learning. In 1 year, from 1663 to 1664, he taught himself everything that was known about modern mathematics.
He knew the problems that the best mathematicians of the age could solve. He knew that he was better than any of them. And I think at that point, he set himself apart from others.
We have to bear in mind that Newton was not a man who found social relations easy. And I think he found mathematics as a métier through which he could live.
In 1664, Newton got his BA and won a graduate scholarship to continue his studies. The following year, plague struck Cambridge. The university was closed, and he returned to Woolsthorpe. Except for a short visit back to Cambridge, Newton was to spend the next 18 months at home, working completely alone. In that time, he made revolutionary advances in mathematics and optics, as well as starting work on his greatest achievement, the laws of gravitation.
Newton wanted us to believe that as he watched that apple fall, he realized that the falling of the apple and the motion of the moon must be similar phenomena. There is, however, no real evidence that Newton had that advanced notion until quite a bit later.
He set the date of 1666 for his discovery to be sure that he would get sole credit for his later work. In the pioneering days of 17th century science, the means of staking claims to discoveries was to publish, something Newton was very reticent to do and later regretted.
He wasn't too concerned with publishing it, making it available to other people, getting glory for his own sake. It was an intellectual challenge that he wanted to deal with.
It was in his mathematical work at Woolsthorpe that Newton's failure to publish was most regrettable. Newton made a number of brilliant discoveries in mathematics, most notably calculus, what Newton called fluxions. The invention of calculus was a major breakthrough in mathematics, allowing measurement of continuously changing motion and the areas of complex shapes. On his return to Cambridge in 1667, he showed a copy of his work on mathematics to Isaac Barrow. It took Barrow 2 years of diplomatic prodding to get Newton to write his first paper, the analysis. Although Newton did allow a select group of mathematicians to see his work, he still refused to publish.
Every discovery that Newton made had two aspects. First, Newton made the discovery, and second, other people had to discover that he had made the discovery.
Apart from his groundbreaking work in mathematics and his growing appreciation for the laws of gravity, Newton also applied himself to the study of light. Of all the mysteries of nature, light and color were the most fascinating to scientists of that time. Newton decided to approach the problem using experimentation and observation, a method of inquiry suggested by Francis Bacon in the 16th century. While at Woolsthorpe, he bought a prism to observe the phenomena of colors.
Having darkened my chamber and made a small hole in my curtains to let a convenient quantity of the sun's light, I placed my prism at its entrance. Isaac Newton, 1666.
What he did first of all was to find out, as far as he could, why the colors are produced.
By using an exhaustive series of tests, he finally whittled down the possibilities to conclude that white light consisted of rays of different colors. Color was a property of light, not of objects.
This particular discovery concerning light and colors explained why we see colored objects. Most important of all, he came to recognize that since a lens is like two prisms, one on top of the other, there'll be color fringes or different refraction of the different colors. And so he decided he would build a telescope in which the magnification was not produced by a big lens, but by a mirror.
Newton constructed the entire telescope by hand, including grinding the concave mirror. In 1671, word of the invention of his reflecting telescope reached the Royal Society. An invitation was sent out to Newton to demonstrate it. Newton was flattered. He built a second telescope and had it hand-delivered to London. It was enthusiastically received. Newton was immediately voted a member. Henry Oldenburg, secretary of the Society, wrote to Newton requesting permission to register the invention. In a rare moment of expansiveness, Newton readily agreed and asked if he could submit a paper in white.
It is the first publication of Isaac Newton. It's the first great scientific discovery to be published in a scientific journal. It's the first great breakthrough that doesn't have any discussion in it of the nature of the divinity, the creation of the world, general metaphysics. It's a straight scientific paper.
Expecting discussion to focus on his experiments, Newton was angered to hear only polite derision. Particularly infuriating were the comments of Robert Hooke, the recognized leader in the field, that Newton had borrowed from his work micrography.
When new discoveries come in science, scientists don't throw away all their cherished beliefs. Only in storybooks does that ever happen. What they rather do is to see whether they can find fault with the new presentation.
The first important discovery of the modern scientific era, using experimental procedures, was met with ridicule by the brightest minds of his time. Newton, who hated controversy, was so disheartened by the criticism that he shelved plans for publication of his work in calculus. In 1676, frustrated by the lack of appreciation for his work, he vowed never to publish again.
I see I have made myself a slave to philosophy. I will resolutely bid adieu to it eternally, except what I do for my private satisfaction. Isaac Newton.
It would be 9 years before he would re-emerge to shake the very foundations of Western thought. In 1669, Newton succeeded Isaac Barrow as Lucasian Professor of Mathematics. As part of the requirement for the post, Newton was to be ordained a minister in the Anglican Church.
Newton, being Newton, approached this problem in a very typical manner. Instead of simply either saying yes or no, he decided he would read up on it.
In his studies of early Christianity, Newton became convinced that the doctrine of the Trinity was a fraud perpetrated in the 3rd and 4th century.
He never, ever could have admitted this in public. It would have cost him his office, bearing in mind, of course, he was a professor at the College of the Holy Trinity in Cambridge. So you could hardly really come up with anti-Trinitarian statements there.
He was set to resign his post when he received a dispensation. It is a measure of the depth of Newton's spiritual beliefs that he was willing to abandon all he held dear rather than compromise them. His belief in God was the very basis of his existence.
He was born months after his father died. Now, in Newton, this takes on an extraordinarily passionate quest for knowing his father's will, the father whom he never understood. God is the Father. God has a will, and it is his duty to search out that will.
Newton's God was a personal God. a creator who was not only over the world, but a part of it, a rational God who revealed himself in the workings of nature. The mechanical philosophy of René Descartes had removed God from nature, something Newton found abhorrent. He turned to alchemy in the hope of finding an answer.
Newton increasingly became worried about the materialistic, atheistic implications of the mechanical philosophy. He was looking for a natural philosophy in which spirit, rather than matter, would be at the center of the world. It's my understanding of his alchemy that he found that in the philosophy of alchemy.
Alchemy was as old as civilization. Essentially, it was the study of natural magic, a search for the spirit in matter. This spirit manifested itself in physical change, such as fermentation of milk to cheese, the curative properties of herbs, or in the transmutation of metals.
Alchemy was concerned with manipulating what were seen to be four elemental properties in nature, the four elements, earth, air, fire, and water, and realizing that these things made all substances, that you could therefore not only make any other substance, such as gold, but you could also somehow learn the secrets by which God had put the world together.
These secrets were revealed only to those who could decipher its arcane language and imagery, as found in the works of other alchemists, such as Hermes Trismegistus, Athanasius Kircher, Michael Myers. Newton believed that he had been ordained to use his God-given genius to reveal this lost wisdom.
He wasn't looking for gold. He wasn't looking for any particular substance. He was looking for the wisdom which the alchemical practitioner believed that you gained once you had learned how matter was composed. It was almost a metaphysical activity.
In 1669, Newton purchased 2 furnaces and converted part of his quarters at Cambridge into a laboratory. Throughout the 1670s and 80s, with the help of his servant Humphrey Newton, he worked long into the night. Humphrey Newton thought him to be a man possessed.
So intense, so serious upon his studies, he ate very sparingly. Nay, oft times he forgot to eat at all. He rarely went to bed till 2 or 3 o'clock, the fire scarcely going out night or day. He sitting up one night as I did another till he finished his chemical experiments. Humphrey Newton.
As intense as his work was in alchemy, mathematics, and physics, it paled in comparison to his studies in theology.
Interpretation of scripture in the 17th century is easily as important for intellectuals as science was. It seems difficult for us to understand that on this interpretation, the whole meaning of existence depends, because works of prophecy are the truth that has been revealed to us.
Hello everyone, welcome to the biggest ideas in the universe. I'm your host, Sean Carroll. Today's big idea, I'm pretty sure, is going to be one of your favorites. It's definitely one of my favorites. The idea is gravity, by which we mean, of course, general relativity, Einstein's theory of gravity. We already mentioned gravity in the context of Newtonian theory. Now we're going to move on to the real stuff. And let me be clear about one of the reasons why this is going to be one of your favorites. Not only is general relativity by itself just a wonderful theory. You know, I wrote a textbook on general relativity, space-time and geometry, which I opened by saying general relativity is the most beautiful physical theory ever invented. And I think that's absolutely true. I'll try to make the case for that. As much as I love quantum mechanics, general relativity is prettier. But the other thing is it's also easier We've been doing a bit of quantum mechanics, quantum field theory stuff, and I understand that a lot of it is abstract and very far removed from our everyday lives and very difficult to get. It's worth it, and I hope that some of the nuances have come across, but it can be taxing, and I completely understand that. Whereas general relativity, even though it has its own mathematical language, and in some ways it is also a little bit removed from our everyday lives, it is easier to understand. Sorry, I'm hesitating because Ariel is complaining in the background, so I'm not playing fetch with her. Sorry about that, you gotta put up with that. This is an irony, of course, because general relativity has a reputation for being incredibly difficult to understand. The old joke is that Arthur Eddington, the British astrophysicist who was a great popularizer of relativity as soon as it came out, he was asked at a talk, I've been told, the questioner says, there's only 3 people in the world who understand general relativity. Can you tell me who the third one is after him and Einstein? And Eddington hesitated. And the questioner says, oh, don't be so modest. And Eddington says, oh no, I'm trying to think of who the third person is. This is not true. It was never the case that only 2 or 3 people understood general relativity. It's a language of mathematics that we need to understand, but we can get there. We can get there faster than most people because you've listened to the previous video that we've had about geometry and topology. So you know something about the geometry of curved space and curved space-time already. So for us, it's going to be a breeze. All right, let's go. So let's think about Newtonian gravity first. We've already talked about Newtonian gravity. Professor Newton told us that the force due to gravity looks like Newton's constant g times one mass m1 times the other mass m2 over r squared. The inverse square law of gravity. So you have 2 objects, there is action at a distance in between them, they pull each other together proportional to their masses and inversely proportional to the distance between them. And then Laplace says that you can think of this as the slope, the force due to gravity can be thought of as the slope of the gravitational potential field. So you have some field, phi, as a function of distance r, and it looks like this, and so you're sitting here, and the slope of that field gives you the force of gravity. It's not a different theory than Newton's, it's exactly the same as Newtonian gravity, but it's put into the language of a field theory, so that rather than simply action at a distance, you have an equation that tells you how the field changes from point to point that is a purely local equation. So that's a step forward. However, this is 1600s, this is around 1800, but then Maxwell comes along with electromagnetism. Okay, Maxwell and other people, but one of the great achievements of Maxwell's electromagnetism in the mid-1800s was understanding that there's a unification of electric phenomena, magnetic phenomena, and also light and radiation. And part of understanding the symmetries of that theory was Einstein's appreciation that the speed of light would be the same to everyone, that you did not need an ether pervading space-time to explain any of it, and the whole theory that we now call special relativity. And the reason I'm bringing these up is, of course, because Newtonian gravity is not compatible with special relativity. So Newton's equation here for the force due to an object with a mass m acting on an object with mass m2, m1 and m2, there's no time in here, the time parameter.
About physics, and typically my book on gravity. Friends and colleagues, I'm delighted to be here talking to you, giving you a very brief tour on gravity. The tour would be very brief. So I'll be talking about my book on gravity. For now, I'd like you to look at this landscape for a minute and ask you if you keep that in mind. Does it remind you of England in any way? So let me start by talking about Newton. Almost basically any talk about gravity would have to start with Newton. Now, in my opinion, physics textbooks have been very unfair to Newton. When I was in high school, I read books and so on and so forth about physics, and typically the books associate him with action at a distance and saying how bizarre a concept that was. Now, as we can see, in 1693, Newton wrote a letter to his friend Richard Bentley. And Newton was perfectly well aware of this problem of action at a distance. And he said something like that gravity should be such that one body could act upon another at some vast distance, like the Earth acting on the moon through empty space without the mediation of anything else, is to me so great an absurdity that I believe no man who has any competent faculty of thinking can ever fall into it. So the strange thing is that physics teachers are trying to teach children about action at distance all the time. So tell me, in school, when you first learned about the inverse square law, did you not find it bizarre that gravity could act through the vastness of space? If you look up at the moon on a nice clear night, it's amazing to think that the Earth, it could actually be pulling the moon down. And so would Newton have described you as lacking in faculty of thinking? Now, who solved Newton's conundrum for him? It took a while. It took more than 100 years. We all know we are here at the Royal Institution, and you all know who that might be. And it's one of my greatest heroes in physics. Well, namely Michael Faraday. This picture was taken from my first popular book, Fearful Symmetry, which was written 35 years ago. Now, I commissioned an undergraduate art student. I put an ad in the student newspaper, get an undergraduate art student to do the drawing. And just this morning, I was just thinking to myself, amazing how time passes by. You know, I wrote this book 35 years ago, and now this young woman undergraduate is now probably like 55, pushing 60. So anyway, I think we all admire, we're all big fans of Michael Faraday here, but the biggest fan of all is Albert Einstein. And read what Albert Einstein has to say. So Albert Einstein said, for us who took in Faraday's ideas, so to speak, with our mother's milk, it is hard to appreciate their greatness and audacity. And that's absolutely true. Me too. I'm a big fan of Faraday. And in my popular books, I put in a picture of Faraday whenever I could, as you can see here. Now, that is high praise in that, indeed, from Albert Einstein, to compare Faraday to mother's milk. And in some way, a theoretical physicist like myself really do think of Faraday's idea as so important to physics, to theoretical physics, that we could compare it to mother's milk. And what is that idea? It is the idea of a field. Okay, so with Faraday, the concept of a field enter into theoretical physics. But now every little kid who watches movies like Star Wars knows about field of force. And in fact, my son, who's now 9 years old, when he was, I remember when he was 4 or 5, he would come over and ask me to use the force on him, the field of force. So all I have to do is stretch out my hand like the emperor, and he would pretend to choke. So what did Faraday say? Let's remind ourselves. Faraday said, two charges do not act directly on each other, but they each produce an electric field that in turn acts on the other charge. And similarly, the magnetic field. So here we have a picture of it. This young woman, Peggy Royster, drew a picture. Here are two charges, a positive charge and a negative charge. And the interaction is that this produces an electric field, which then acts on the negative charge. Now, a pragmatic physicist, and you'll be amazed, actually, among the physicists I know, it's incredible to me, actually, how many physicists are so incredibly practical-minded. If there's some idea that doesn't have any utility to them, that they cannot use it in some way, they kind of just don't care about it or dismiss it and so on. They don't even want to hear about it or want to learn about it. You'll be amazed at how many physicists out there working on very specialized stuff doesn't know a thing about Einstein's theory of gravity. This is always an astonishment to me. Now, a pragmatic physicist would be inclined to dismiss all this as just talk. You know, this is worthless stuff. You know, it doesn't advance our knowledge one bit. It's just another way of describing Coulomb's law. But this pragmatic view misses the point. And the important point I'll come to on the next slide. So what's the important point? The real content of Faraday's picture is that the electromagnetic field not only can be thought of as a separate entity, it is a separate physical entity. It can move off on its own. Now, a friend of mine, Anupam Garg, written a textbook on electromagnetism, and his book, he made the following statement just to emphasize this point upon students. He said the electromagnetic field, and I quote, the electromagnetic field is as real as a rhino. Think about that, okay? It's no less real than a rhino. The electromagnetic field, like young people today, could leave home, take off, and live independently of the charges and currents that generated it. That's one of the great discoveries of Maxwell, that this field could literally take off. Without it, our modern civilization would be totally impossible. The age of telecommunication is completely based on this statement. Now, England produced these two great physicists in the 19th century, Faraday and Maxwell. And the interesting thing is that they couldn't be more opposite. As you probably all know, Faraday came out of abject poverty, almost Dickensian. He had no education, so he knew no mathematics. And one of the reasons he invented this idea of the field, which now has become part of physics everywhere. I work on quantum field theory, and I'm sometimes described as a quantum field theorist. That's my main profession, so to speak. On the other hand, Maxwell grew up in a rather distinguished family, I think one of the more distinguished families of that time. But when Maxwell saw what Faraday had written about fields, he vowed not to read any mathematics until after he had understood what Maxwell had to say. So this I love to show to the young theory students today. You know, so for a while, for example,
You may live in a different time zone than I, but 1 hour for me is 1 hour for you. An hour might feel longer if it's a job interview, but even the most awkward conversation doesn't actually slow down time. And yet, Einstein said, time can slow down. It doesn't always pass at the same rate. Just what did Einstein say about the passage of time? What's the resolution of the twin paradox? What's up with Newton's bucket? And what does it all mean? That's what we'll talk about today. When I was a teenager, I was super interested in Einstein's theories of space and time, and I read a lot of popular science books about them. I didn't understand a thing. I then went on to do a PhD in physics, and today it's my turn trying to explain it to you. The most important part of Einstein's theories is that they combine space and time to one common entity, space-time. This idea didn't come from Einstein, but from Minkowski, but Einstein was the one to understand what it means. Which is why today you can buy a bobblehead Einstein and not a bobblehead Minkowski. Sorry, Minkowski. Einstein was the one to understand that if you combine space with time, then time becomes a coordinate, like space. That space is a coordinate means we can put distance markers on it, and we can choose them as we want. Once we have chosen some agreed upon markers, we can use them to communicate where we are. You can give me your GPS coordinates and I'll know where to find you. But those coordinates don't tell me what the length of the path is that'll take me there, because there could be many different paths. The coordinates alone don't tell me. If time becomes a coordinate, the same happens to time. If you give me your coordinates in space and time, I will know where and when to find you. But the coordinates don't tell me the length of the path that brings me there, and they also don't tell me how long it'll take me to get there. Wait, you may say, if it's 5 a.m. now and I tell you we're meeting at 5 p.m., then that'll take 12 hours, right? No, wrong. Those 12 hours are your coordinate time. They are just convenient markers. They are convenient for you because they agree with the time that actually passes for you. But how much time passes for me while I get to our meeting depends on how I get there. It's just that the difference between the passage of your time and my time as I come to meet you is normally so small we don't notice. It'd only become noticeable if I was moving close to the speed of light and my doctor advised me against it. If you've been keeping track, 3 dimensions of space plus 1 dimension of time makes 4 dimensions. Unfortunately, YouTube doesn't support 4D graphics, at least not yet, so we'll have to settle on just 1 dimension of space and 1 dimension of time. Just imagine that it describes something that can move only left or right, like American politics maybe. Here's what this space-time looks like. Not particularly impressive, I know. Actually, it looks exactly like it's just 2 dimensions of space, like a map or something. That's what it looks like, but looks can be deceiving, and in this case they are. For one thing, in space-time, if you don't move, then you still make a line, namely one that just goes straight up. If you move at some constant velocity, then you can describe that by a straight line tilted at some angle. By convention, a 45-degree angle marks the speed of light. Why 45 degrees? Why not? Maybe it's physicists' idea of having fun. But more importantly, space-time differs from space in one crucial way, which is how you calculate distances in it. If you have 2 dimensions of space, one called x and the other y, with 2 points in them, then calculating the length of a straight line between them is straightforward. You take the distances between the coordinate labels of x, call that delta x, and the same for y, call that delta y. And then the distance between the points is the square root of the sum of the squares, as we learned in kindergarten. This is called the Euclidean distance. In space-time, it doesn't work like this. In space-time, we deal with combinations of coordinates in space and time, which we call events. If you have 2 events, each with a position in x and a time in t, and you want to calculate the space-time distance between them, then again, you take the differences between the coordinate labels. In this case, that's delta x and delta t. And then you take the square root of the square of delta t minus the square of delta x divided by c, where c is the speed of light. This minus makes all the difference. Basically, the rest of this video is to explain what the consequences of this minus are. This is also called the Lorentzian distance after Hendrik Lorentz. That's Lorentz with TZ. Why is there a minus there? Because it works. This is how theories in physics come about. You have an idea, you check the predictions, you stick with your idea or toss it out. This one was a keeper. To see what this means, let's look at points that have the same distance from a reference point that will take to be the origin of the coordinate system. Let's say, for example, the distance is equal to 1 in whatever units you have chosen. If these were coordinates in a two-dimensional space, then all points at the same distance from the origin would be on a circle. Different distances correspond to circles with different radii. But if you do this in space-time, then all points at the same space-time distance from the origin are hyperbolic. You can't move on those lines because that would require you to move faster than light, but you could move on those. That would require a constant acceleration. The key to making sense of space-time is now this. The time that passes for an observer moving on any curve in this space-time is the length of that curve, calculated using this peculiar notion of Lorentzian distance that we just discussed. It's called the proper time. It's the proper way of calculating time according to Einstein. If you move between two events at constant velocity, then the time which passes on the way is, as we previously saw, the square root of delta t square minus delta x over c squared. If the observer doesn't move on a straight line, you break up the line into small straight pieces, sum over them, and take a limit, so you integrate over the curve. Don't worry if you don't know how to do that integral. There's no exam at the end of the video. You just need to know that this peculiar distance in space-time measures how much time passes as an observer moves from one event to another. The time that passes between two events is not the time on the coordinate axis. That's just a label. It's convention. It has no physical meaning. So the consequence of making time into a coordinate is that the physically relevant time becomes a personal thing. It depends on how you move around. In the special case when an observer sits still according to the space coordinates, the time that passes for them is the same as the coordinate time, because then you have the proper time is the square root of the square of delta t, which is just delta t.
In the spring of 1905, a storm broke out in the mind of Albert Einstein. At least that is how Einstein himself described it later in life. And the result of that storm of thinking is the special theory of relativity. A theory that completely transforms our understanding of space and time and matter and energy. I mean, Einstein found, completely counter to experience, that clocks in motion tick off time at a slower rate. He found that objects in motion are contracted along their direction of motion. He found that clocks, that one set of individuals say are in sync relative to each other, he found that if someone's moving relative to those clocks, they would say they're not synchronized. And of course, he also found the most famous equation in all of physics, E equals mc squared, establishing this deep, hidden connection between mass and energy. Now, you should say to yourself, if there is such an unexpected nature to reality that we have missed through our everyday experience, why have we missed it? I mean, why aren't we aware of special relativity right in our bones? And the answer to that is, when we look out at the universe, we recognize that there are a huge range of scales that constitute reality. And we humans only have access to a very small part of that totality. So to give you a feel for that, let's look at one axis, a length axis. And if you look at the scales that are out there in length, atoms, 10 to the minus 10 meter, viruses, 10 to the minus 8 meters, red blood cells, 10 to the minus 6, single-celled organisms, there we humans are, 2 meters, the Earth, 10 to the 5 meters, solar system, 10 to the 13, galaxy, and on to the observable universe itself. A huge range of scales when it comes to length, and we humans really only have direct access through experience to a small part of that. And that's only the axis of length. Imagine we look at the axis of mass. There too, we will find a huge range of scales, right? So if we go back and look at atoms, They weigh in 10 to the minus 26 kilograms, go down to red blood cells, 10 to the minus 15. Humans, well, depends who you're talking to, but about, 100 kilograms or so. Solar system on to the entire universe, the observable part, 10 to the 52 kilograms. A huge range of scales in mass. We humans only have direct access to a small piece of it. One more axis to look at is the axis of speed. So we humans, we walk around the world at certain ordinary everyday speeds. Sometimes we go into airplanes, but there's a huge range of speeds out there. The growth of human hair, that's pretty small. Human speed, typically, space shuttle, 10 to the 3 meters per second, speed of light. That's a number that's going to come up a lot in our discussion, 10 to the 8 or so meters per second. The point is, in this spectrum of all possibilities, in length, in mass, and also in speed, we humans occupy a tiny, tiny part. So our experience, the experience that has given us our intuition, is built up from very limited sense of what is actually out there. So our intuition, which really has come in some sense from evolution, right? So we evolved out there in the jungle, and our intuition got built up in order that we can survive. The survival value of understanding your environment is what matters. We humans only have access to a small piece of the totality of what's out there, and therefore it would be surprising if what we have experienced really does tell us about the physics at all possible scales, in length, in speed, and in mass. And it turns out that indeed it is the case that when you look at extremes of mass or length or speed, the world operates, the universe operates in ways that we are not accustomed to. If you are looking at extremes, say a very small size, the new physics that comes into play is called quantum mechanics. If you are looking at extremes of huge mass, the new physics that comes into play is the general theory of relativity. If you are looking at extremes of speed, how the universe behaves at very, very high speeds, then it is the special theory of relativity that comes into play. That is what we are going to be discussing. So in a nutshell, all of the discussion we are going to be having here is focused upon how the universe behaves at very high speeds. That is the special theory of relativity. Since speed is the fundamental core of what drives the special theory of relativity, let's start at the beginning and ask the most basic question of all, which is, what is speed? Well, we all know the answer to that, but let's get all on the same page. So if that car, say, has a speed of 100 kilometers per hour, we all know what that means. If we look at how far it's gone divided by how long it takes it to get there, so let's say this is 1 hour journey. If it's going 100 kilometers an hour, we know that it will have traveled 100 kilometers in that hour. That's what speed is. So in essence, speed is nothing but distance that an object travels divided by duration. Now, expressed in that language, speed might seem like, I don't know, a kind of boring concept, a pedestrian concept. Why concern yourself with speed? The answer to that is clear if we recognize that distance is a measure that has to do with space. Duration is a measure that has to do with time. So if we find, as we are going to find going forward, that speed has unusual features when the speeds involved get very big, near the speed of light, what we really will therefore be learning is that space and time have weird, strange features. That is what we are after. Okay, good. That's where we're headed. Let's start by first thinking about the non-strange features of speed, the features that we all hold in our intuition. So what are the basic features of speed? Well, first off, speed is a concept that even before Einstein was known is a concept that is relative. What do I mean by that? Well, imagine we look at this car, say it's going 100 kilometers per hour. What we need to say is 100 kilometers per hour relative to the road. Why? If that road is itself moving, let's say it's on a boat, the boat is moving, then the car's speed relative to the water is not 100 kilometers per hour. And if we zoom out and look at that car on the surface of the Earth, and we realize that the Earth itself is spinning around, the Earth itself is going in orbit around the sun, with respect to the frame of reference, our perspective right now, that car is executing a pretty complicated motion, not just 100 kilometers per hour. So it's always vital when you're talking about speed to recognize that you can only ever frame the idea of speed for ordinary objects that we encounter as the object has this and that speed relative to this or that object. You need to specify the reference in order that the speed that you are specifying has any meaning at all. Okay, so that's a very basic feature of speed, that it is relative. Another basic feature of speed is that it is additive and subtractive. So what do I mean by that? Well, let's imagine that we have two characters who are playing a game of catch with, say, football. George and Gracie, two characters that we are going to encounter often in our discussions. And imagine that they're throwing that football back and forth at, say, 5 meters per second. Now, that's all well and good, completely understood, but let's imagine that they go out to play a game of catch on another day, and Gracie is surprised to see that George has a hand grenade. Now, she doesn't like hand grenades, and so she runs away when he throws it because she knows that by running away from the hand grenade, she can change the speed at which it approaches her. She can subtract her own speed from the speed of the oncoming grenade, and that way have it approach her not, say, at the initial speed at which it was tossed, which, for instance, might be just like the football, 5 meters per second. Instead, if she runs away at 3 meters per second, she knows that now the grenade will approach her more slowly at 2 meters per second. And that is a good thing when it comes to hand grenades. Similarly, it's the case that if an observer like Gracie is to not run away, but say run toward an object that is being thrown at her, the speed with which she approaches the object will be added to the rate at which it approaches her. So if it was thrown at 5 and she's running toward it at 3, well, we all know that that means it will approach her at 8 meters per second. Speed is additive and subtractive. You can change the speed with which an object is coming toward you by either running toward it or away from it. Now let me quickly mention, just as a small footnote, these basic calculations that we've done here, we surprisingly are going to find that they are only approximate when you take into account some of the strange features of relativity, but that's something that we will encounter later, especially if you're doing the math version of this course. But in terms of the basic idea that comes from our intuition, you certainly would anticipate that if you run toward an object, its speed will approach you more quickly. If you run away from an object, it'll approach you more slowly. Third basic feature of speed that, again, we are all familiar with is this. When you are executing a very special kind of motion, what we call constant velocity motion, motion that has a fixed speed, fixed magnitude, in a fixed direction, then you can't feel that motion, right? You can't feel that motion for a very good reason. If you are executing constant velocity motion, you are completely justified in claiming to be at rest and the rest of the world moving by you. In that sense, constant velocity motion is very special because it is motion that is completely subjective. There is no absolute notion of being in motion when the velocity is constant. So let me give you a quick example of that. So let's imagine that we have one and the same physical situation described from two different perspectives. So what I'm going to imagine is having George and Gracie floating in space, okay? Floating in space. Now here's George's view of the events. He looks out and he sees a character, Gracie, coming toward him, and she waves as she passes, as does he. His perspective is that he is stationary and she is rushing by him. Good. Now I'm going to show you exactly the same situation, but from Gracie's perspective. So what does Gracie say? From her perspective, she says that she is stationary out there in space. She looks out into the distance and she sees George rushing by. He waves, she does too, and he goes on his merry way. Is one perspective right and the other wrong? Absolutely not. You are completely justified if you're not accelerating, if you aren't changing your speed or changing the direction of motion, to say that you are stationary. Now, the reason why I'm emphasizing constant velocity motion is something that you have all experienced, right? If you are in a car and you take a sharp turn, you feel your body being pushed this direction, you know that you are moving. If you are in an airplane and it's taking off, as it accelerates, as it speeds up, you feel yourself pushed back into the seat. You know that you are in motion. But if you're not accelerating, you don't feel the motion, and in fact, there is no way for you to detect the motion at all. So for instance, if you imagine that George and Gracie were in two floating laboratories out there in space, and they do experiments to work out the laws of physics, they will work out exactly the same laws because there will be absolutely no remnant, no experimental implication of their relative motion if that motion is at constant speed in a fixed direction. No way to determine your state of motion because you are justified in saying that you are at rest. Now that idea that you can claim to be at rest, that there's no implication of constant velocity motion, does not start with special relativity. It does not start with Albert Einstein. This is an idea actually that goes way, way back. It goes all the way back to Galileo. And Galileo wrote a wonderfully poetic description of this idea. Let me show you a little visual representation of what he said, and I'll just read his words to you while this plays. So he said, "Shut yourself up on a large ship, and there procure gnats, flies, and other small winged creatures. He said, let a bottle be hung up, which drop by drop lets forth its water into another narrow-necked bottle placed underneath. Then, with the ship lying still, observe how the winged animals fly with like velocity toward all parts of the room, how the distilling drops all fall into the bottle placed underneath. Then, he says, having observed all these particulars, make the ship move with whatever velocity you please." So here it is, the ship is going into motion, and he says that so long as the motion is uniform, by which he means constant velocity, you shall not be able to discern the least alteration in all the forenamed effects, nor can you gather by any of them whether the ship is moving or standing still. That is the very same idea, that constant velocity motion cannot be detected, it has no impact on your observations. Old idea, back with Galileo. So where then does Einstein come into this story? Einstein's new contribution is to say that among the four named effects that Galileo was talking about, he was just talking about the gnats and flies and the water dropping into the bottle placed underneath, that those things would not change if you go into motion so long as it's uniform. Einstein added something to the list. Einstein added to the list of things that would not change, he added the speed of light. This is the surprising new insight of Einstein. Let's see what it means. The speed of light is constant, right? That is one of the most famous sentences in all of science. The speed of light is constant. Now, what does it mean? And why should you care? Well, to get there, let's think about how it is that Einstein came to this idea that the speed of light is constant. It's an interesting history where over the course of many centuries, many people